So this is kind of where we ended last class. We had derived the stress mathematically from the little Cauchy tetrahedron, and we didn't go through all the work, but I mentioned that due to this conservation of angular momentum, the stress tensor is symmetric, and so here's the symmetric realization of the stress tensor, and then we went on to start to talk about where am I at? Well, this is where I wanted to be. So this is the very last slide we talked about last time, and we talked about there's a way to sort of diagonalize the stress tensor. And what this has to do with, this is actually true for any kind of matrix, but what we're actually talking about here in terms of stress is that the diagonal entries of the stress tensor we call normal stresses, okay? And the off-diagonal entries, those ones that are symmetric, we call them shear stresses, okay? So normal stresses are the stress, or the part of the stress tensor that contributes to the volume change of a material, right? So if I have a block of material and I squeeze it and I change its volume, that's due to normal stress, okay? Shear stresses have to do with shape change, right? So if I have a block of material and I sort of grab the top and the bottom and shear it such that it turns into a little parallelogram or something like that, that's a volume change, and those are associated with shear stresses. But we also learned that the stress tensor is coordinate frame dependent, right? So if that goes back to that example where we had our 1D bar from you had the stress is equal to F over A, where A is defined as a perfect cross section here. But if I chose to cut this at an angle and I wanted to know what the stress was with respect to that area, then there's obviously something different because it's the same force and it's a different area. So this really has to do with my choice of coordinate system. In the first example, my coordinate system is perpendicular to the bar, right? So my coordinate system is like this. And in the second example, my coordinate system is like this, okay? And if I rotate through the coordinates correctly, if I take care of everything correctly, then I can see that they're related to one another, okay? So the point here is just know that the stress tensor is coordinate frame dependent, okay? If you have a different coordinate frame, then you're going to get a different answer, or a different stress, rather. And so what we want to do here, what we want to realize here, is that there is a preferred coordinate direction in which the stress tensor will be diagonal, okay? So if we can just figure out what those directions are, we can take our complicated stress tensor that has entries everywhere, right? And we can rotate it into the proper frame such that it can be described perfectly by a diagonal entry. So it sort of makes it simpler, okay? And the way we do that is through this sort of so-called eigenvalue decomposition, right? So in the linear algebra lecture, there was at least a real overview, high-level overview of what eigenvalues and eigenvectors are. And in this case, these Q's are a matrix of the eigenvectors. So there'll be 3 eigenvectors, and if you place them as column vectors into a matrix, so you have a 3×3 matrix of the eigenvectors, then this transformation, where this is the stress tensor, the full stress tensor, this transformation will lead to this S prime, which will have the eigenvalues on the diagonal, okay? So in order to do this, we have to solve an eigenvalue problem. The last thing I want to point out is in the linear algebra lecture, it's likely, I think that this term right here, it may have been Q transpose. Okay, and here I have Q inverse. So I guess Q inverse is the more general, but if Q is what we call an orthonormal matrix, or also a unitary matrix, all that means is that the eigenvectors are unit vectors, right? So you just divide out the magnitude, right? So if each of the eigenvectors are unit vectors, right, the magnitude's been divided out, then Q will be a unitary matrix, and a unitary matrix, its inverse is its transpose. Okay, and so that makes it much nicer. If it is unitary, then it's much nicer because you don't have to actually go through all the complicated steps of computing the matrix inverse. You can just transpose it, which is much easier. Okay, so let's work an example.